You ever see those mind-blowing simulations of galaxies colliding or how scientists predict global weather patterns? They do it with supercomputers, which really are just thousands and thousands of computers all networked together. But how in the world do you get them all to cooperate on one single massive problem? Well, today, we're going to unlock that very secret. So that's the fundamental challenge, right? It's the core question of parallel computing. You've got all this incredible processing power at your fingertips, but you need a language. You need a set of rules for them to follow so they aren't just, tripping over each other. And the answer really comes down to how they share information. And there are basically two main ways to build these parallel machines. The first is shared memory. You can think of this like one giant whiteboard that everyone in a room can write on. It works great for a small team, it's pretty simple. But imagine thousands of people all trying to use that one whiteboard at once. Total chaos. The other way, distributed memory, gives every single computer its own private little whiteboard. Now, this scales up beautifully, but it creates a whole new problem. How do they talk to each other and share what's on their boards? The solution is a concept called message passing. And honestly, it's pretty much exactly what it sounds like. One process bundles up some data, calls a send function, and another process somewhere else calls a receive function to grab it. This is the absolute foundation of how they coordinate their work. And the industry standard for doing this is something called MPI, which stands for the Message Passing Interface. Okay, theory is great and all, but let's actually see what this looks like in practice. We're going to build the classic first program everyone writes, Hello World. But we're going to do it with a parallel twist. We'll have one main process, and all the other processes are going to send it a little greeting message for it to print out. Pretty much any MPI program you'll ever see has these 5 essential steps. First, you have to initialize the whole system. Wake it up with MPI init. Then, each process needs to figure out 2 things. Who am I? That's its unique ID or its rank. And how many of us are there in total? That's the size. Then, based on its rank, it does its specific job. Maybe it sends a message, maybe it receives one. And finally, when everything's done, you shut it all down cleanly with MPI finalize. This brings us to this really, really powerful idea called Single Program Multiple Data, or SPMD. Now listen to this. You don't write 1,000 different programs for 1,000 different computer cores. No way. You write one single program. And inside that one program, you have logic that says something like, if my rank is 0, my job is to be the manager. Otherwise, if my rank is anything else, I'm a worker. It is an incredibly elegant way to control a massive, complex system from just a single file. Okay, so saying hello is cute, but let's be honest, it doesn't exactly require a supercomputer. So let's apply these new concepts to a real-world problem, calculating the area under a curve. We're going to use a method called the trapezoidal rule, and we're going to do it in parallel. So here's the game plan, and it's pretty straightforward. We'll take the problem, the curve, and slice it up into a bunch of little pieces. We'll give each of our worker processes its own tiny slice to analyze. Each worker calculates the area for its little piece and then sends that single number over to our manager, which is process 0. Process 0 just sits there, collects all these partial results one by one, and adds them all up to get the final total area. Simple, logical, makes sense. But hold on a second. Does that sound super efficient to you? Having one poor process listen to maybe thousands of other processes, one at a time. This creates a massive traffic jam, a huge bottleneck. As we add more and more workers to solve the problem faster, our manager just gets more and more overwhelmed. Our simple logical solution actually has a fatal flaw. Luckily, the people who designed MPIs saw this problem coming a mile away. They gave us a much better way to handle it: collective operations. So instead of clumsy one-to-one messaging for tasks that involve the whole group, we can use these highly optimized functions where all the processes work together as a team. This right here is where the real power of MPI starts to shine. And here are 2 key collective operations that completely solve our problem. To start the calculation, process 0 can use MPI bcast to broadcast the initial problem parameters to everybody else, all at once. It's like a manager giving a single briefing to the whole team. Then, at the end, instead of sending all those individual results, everyone participates in an MPI reduce. This function intelligently combines all the little partial sums using a super efficient, often tree-like structure to get the final answer back to process 0 without that terrible bottleneck. So why is this so important? I mean, why not just write the code to do this yourself? Well, this quote from the source material absolutely nails it. MPI provides these powerful collective functions because figuring out the absolute fastest way to sum a bunch of numbers across a specific supercomputer's unique network hardware, well, that's an incredibly hard problem. MPI handles all that crazy optimization for you, so you can just focus on your science. So after all that theory, after all that work to switch to these smarter functions, what's the actual payoff? Was it worth it? Let's take a look at the numbers from a different but very common parallel computing task: matrix vector multiplication. Okay, this table shows something called speed up, which is just how many times faster our parallel program is compared to running it on just one process. Now just look at that rightmost column for the biggest problem size. With 2 processes, we're almost exactly 2 times faster. With 8 processes, we're nearly 8 times faster. And with 16 processes, we get a speed up of 15.5. That is a phenomenal result. It's almost perfect. And here's that same data visually, which makes it even clearer. You can see the bar is climbing almost perfectly in line with the number of processes we throw at the problem. This is what parallel programmers absolutely dream of. It's called near linear speedup, and it means our parallel strategy is working beautifully. Adding more computers is actually giving us an almost proportional boost in performance. And this leads us to the absolute holy grail of parallel programming: scalability. An algorithm is called scalable if its performance keeps getting better as you add more processors to tackle a bigger and bigger problem. This ability to maintain high efficiency is the true sign of an effective parallel program, one that can really take advantage of a massive supercomputer. So, we've built this powerful tool for cooperation. We figured out how to make thousands of processes work together. But in doing so, we've also created this incredibly complex system of communication. What happens if, say, 2 processes try to send messages to each other at the exact same time? Could they get stuck waiting for each other forever, creating a digital gridlock? Well, that's the next big challenge in mastering the world of parallel computing.